When we have a set of scattered data points, drawing a smooth curve through them is more than a matter of aesthetics. It's a challenge of numerical stability. This is what happens when we try to connect 10 points with a single high-degree polynomial. While it hits every point, the edges whip wildly up and down. This instability is Runge's phenomenon, and it makes high-degree polynomials practically useless for complex data. We could simplify things by using linear splines, essentially connecting the dots with straight lines. But these segments create sharp corners. Mathematically, these points are non-differentiable, meaning the velocity of the curve changes instantly and unnaturally. The cubic spline solves this by using a third-degree polynomial for each individual gap. A degree of 3 is high enough to ensure the slope and the curvature match at every connection point, but low enough to prevent the chaotic oscillations we saw earlier. By moving to localized cubic pieces, we can manipulate specific points without distorting the entire shape, keeping the curve smooth and predictable. Theorem 6.6-1 provides the mathematical proof that exactly one unique cubic spline exists for any dataset. It begins by partitioning the axis into gaps between points. Within any interval, the polynomial is defined by 4 constraints: function value and first derivative at both endpoints. To make the transition between these segments invisible, we require c-squared continuity. This means the second derivative, the rate at which the curve bends, must be the same for both the segment ending at a node and the segment beginning there. Applying this matching requirement to every node in the sequence transforms the geometric problem into a large system of linear equations. Because the diagonal values of this specific matrix are strictly greater than the sum of their row, it guarantees the matrix is invertible. It proves we can achieve c-squared continuity, where every segment transition is visually seamless, by simply solving a stable system of linear equations. The name spline comes from the physical world. Before digital design, draftsmen used flexible wooden rods to trace smooth curves for holes and airfoils. These rods naturally minimize their internal strain. Mathematically, we represent this bending energy as the integral of the squared second derivative. A higher value here means the curve is under more physical stress. Using integration by parts to compare a spline to any other curve, boundary conditions at the anchors cause extra evaluation terms to drop out entirely. This leaves an inequality proving the cubic spline has the smallest possible integral, the flattest possible smooth curve. The math of functional analysis confirms that the curve produced by our matrix is the same shape a physical rod takes when it naturally finds the path of least resistance. Because Theorem 6.61 provided a reliable, unique solution, engineering was able to move from physical wood rods to digital CAD systems, calculating these shapes instantly on screen. Looking at the hierarchy of interpolation, cubic splines offer the ideal balance. They avoid the chaos of global polynomials and the sharpness of linear ones, providing both local control and second-order smoothness. This entire system relies on a single, stable matrix inversion, making it one of the most computationally efficient ways to model a smooth path. Cubic splines show that the most effective way to solve a broad, global problem is often to break it into localized pieces that are perfectly connected.